Maybe somewhere in your mathematical past, it's possible that you might have discovered a formula involving work and vectors, where the work done for moving something from place A to place B is the dot product of the force vector, which could be variable, and the vector that represents the path along which the object is moved. But then, what if the path is not moved on a straight line from place A to place B, but maybe on some other kind of smooth curve? And that's what line integrals are all about. The hardest part, perhaps, in working line integrals is to somehow create a vector valued function that describes the path. And if you have a piecewise smooth curve, and you can define that as you can see the definition of it here, smooth, it's smooth if the derivatives of the I part and the j part are continuous on an interval and not simultaneously zero on an interval. So similarly with a space curve, the derivatives of the I, j, and k parts must be continuous on the closed interval and not simultaneously zero on the open interval, in which case the curve is considered piecewise smooth. And if that can be partitioned into a finite number of subintervals, on each of which the curve itself is smooth. For example, here's one below, and you'll see, I think, the difficulty in the parametrization of this curve. It starts out at 0, 0, although I don't have anything marking that that's the starting point, goes up to the point 4, 3, down to the point 4, 0, and then back to the point 0, 0. So we'd like to find a smooth parametrization of that curve. Well, it's not too hard to see the C1 from here to here, 4ti plus 3tj, t going from 0 to 1. When I drop back down here, the x part, or the I part I should say, is a constant at 4, and the j part starts at 3 and ends at 0. So if we could say this is 4i minus 3 times tj, where t goes from 1 to 0. That, maybe you'll see, does create a little bit of a conflict. Actually, I guess that would be t going from -1 to 0. That would work, right? Because you want to start at 4, 3. So t going from -1 to 0. And maybe this would work if we somehow started C3 from here to here. It's just 4ti because the j part is 0 on the whole path. And -4ti would be good, and we started at 4 and we wind up at 0. So maybe starting with t equals -1 and winding up at t equals 0, or something like that. That at least describes these three curves, right? These three paths. And you could make a case for, well, that could be 4ti, but then t would be going from 1 to 0, but it'd be going backwards, so that's a little awkward. So we have our awkwardnesses and our not awkwardnesses, but there is a way to do that, but it's not described as one continuous parametrization. It's just that describes each of these three pieces. Is there a way we could put that all together? And the answer is yes. This one, we nailed that already. 4ti plus 3tj, t going from 0 to 1. Here it is. But when we look at this path, of course we already nailed the fact that the I component is going to be a constant at 4i, but now plus 3 times 2 minus t, t going from 1 to 2. See, we need to start at 1 and work our way up to maybe 2. This is time units. It could be seconds or minutes or hours or whatever, but if we start at t equals 1, then that's 3 times 2 minus 1, which is 3 times 1, which is 3. And working our way down to when t equals 2, we want that to be 0. So when t equals 2, we got 3 times 2 minus 2, which is 3 times 0, so we got 0j. So there's that part, t going from 1 to 2. And then we want to start here and come back to the origin. And so, again, the j part is 0 for sure. And here's the tricky part. We want to start at t equals 2 seconds. So that would be 3 minus 2. So 4 times 1, I, that's here. And then we want to say, yeah, but we want to continue until t equals 3. And so when t equals 3, we'd have 4 times 3 minus 3, which is 4 times 0, which would be 0i, so we'd be back at the origin again. This is one of many possible parameterizations of this curve. I just thought I'd try to pick the simplest one, and it's kind of nice in that I start at 0 for t, and I go all the way up to 3, including both endpoints, and I don't have any overlapping problems, because this is less than or equal to 1, and this is greater than 1. So there's a very nice parameterization of this curve, right? And that might be the hard part of many of these problems. Okay, so what then is a line integral? Well, up to now, let's put it in the next video.